Hello and welcome back. This video will be on section 2.2 on histograms. So if you remember from the previous videos, we looked at frequency tables. So this was an example of a frequency table that we saw where we had some test scores from a course, and we counted how many test scores fell into each of these ranges, and each range we called a class. This is nice, gives us a lot of information, but one helpful trick is to display this data in a graph, and it's a little bit easier to read rather than just seeing these individual numbers here. And I'm going to do this very intuitively, and you'll see that histograms, the kind of graph I'll make, is essentially the right choice for displaying this kind of data. So we'll do this in a way that will make sense. We have 5 ranges of data, so we'll split our x-axis, the horizontal axis, into 5 equally sized ranges. Note that each class is exactly 10 wide. They're all the same, so they should be the same along the horizontal axis. And then we should label the dividing marks with the class boundaries. So remember, the class boundaries fall in between the classes, and from what we saw last time, these will be 49.5, 59.5, 69.5, 79.5, 89.5, and 99.5. So here were the class boundaries, and then the heights will simply be the frequency in here. So we can label this with 2, 4, 6, 8. And the first class that we see from 50 to 59, there were 2 test scores within that range. The same with between 59 and 69. The next range bumped up to 5. The next range was all the way up to 8. If I could draw in straight lines. And the last was at 7. So this is a histogram. There's a few rather important features of this. Note that each bar will have equal width. We don't want to put more. We don't want any one range, any one class to be larger than any others, because they should all have the same width. And they're adjacent to one another. They abut one another exactly. There's no gaps in between there. And this is to say that we are capturing all of the data. We're not missing any data in between here. The horizontal scale will be the classes. And the vertical scale will be all of the frequencies. Now, the thing is, in a histogram, we can label this with the frequencies as the height, or we could make a different graph with the relative frequencies as well if we wanted. The relative frequencies being the percentages of things in each class. The nice thing is that it's really easy to make one because the graph doesn't change. The relative heights of each of the bars are going to be exactly the same. It doesn't matter if you use the frequencies or the relative frequencies. The word relative, meaning relative to one another, won't change when we're displaying the data. So you can either use the frequencies or the relative frequencies when you're displaying this data. The frequency will give you a little bit more information, because if I told you that 33% of the data fell into this range, we know that 33% of the data was in that range. We don't know specifically how many were. So while the shape of the distribution doesn't change, frequencies will tell you a little bit more information than relative frequencies. Histograms help us with a couple of things. We can see the shape of the data, the spread, and figure out where the center of the data is, and we can see if there are any outliers in the data. So notice that all of these bars are at least some tall. We don't have any gaps in the data. There are no classes without any members. So we can tell a lot by looking at histograms. And there are a few common shapes of distributions, and I will show a picture of some of these in a second. So there are normal distributions, which are the usual bell-shaped distributions, and these are meant to be very symmetric. Uniform distributions don't have the rise and fall like a bell, so whereas a bell might look something like that, a uniform distribution will look, it's meant to be perfectly flat and level. A skew distribution is one where it will have a little bit of a tail. So you can imagine kind of like a bell-shaped, but maybe it extends off to one side, or it extends off to one side in the other direction. Because this has a right tail, this is skewed to the right. Since this has a left tail, this is skewed to the left. And to show you a quick picture of some of these, we can look at this. So this is just coming exactly from the textbook. And so this first shape here is just going to be a normal distribution, so it's a bell-shaped. And you can see how it's roughly going to be symmetrical. Now this isn't perfect, as in it's not exactly this nice smooth line, but data in real life won't quite be this nice smooth straight line. We'll have a little bit of bumps in there. This next one is a uniform distribution. Note how it's almost completely level at the top. This is something, again, it's not perfect. We've got a little bit of a wiggle, but it's close enough that we could assume that this is going to be a uniform distribution. Next, we have some distributions that look kind of bell-shaped, but with a longer tail sticking out either to the right or to the left. So the light blue one, where I'm tracing now, is skewed to the right because it has a tail that extends to the right. Over here, this darker brown one, we have a tail that extends to the left. So this is a tail, so this is a distribution that is skewed to the left. Whatever side the tail is on, that's the skewness of the data. This is whether or not it'll be skewed to the right or left. Depends on if it has a tail that extends to the right or to the left.